Hi, I'm Joe Quirk. Welcome to the Blue Frontiers podcast about all my favorite things: seasteading, the environment, special economic zones, and innovation in science, technology, governance, and society itself. Chien Ming Wang is one of the leading very large floating structure experts in the world. He's from Singapore. He's advised us over the years, telling us, you still need to do this and you still need to do that. And then at the first Tahitian seasteading gathering, he said, I'm really proud of you. That was one of the most satisfying moments of my life. Enjoy your conversation with Chien Ming Wang.
Hello, seasteaders. I'm here with Professor Wang. He is a Transport and Main Roads Chair Professor in Structural Engineering. How are you, Professor Wang?
I'm very fine. Thank you, Natalie. Good to see you. Yes, it's a beautiful day today to speak on floating structures.
And I'm keeping you inside.
All right.
So, Professor Wang, what is the difference between a very large floating structure and a not so large floating structure?
Well, that is very much to do with the size, the dimensions.
Okay.
If you have very, very large floating structures, we are talking about, in hundreds of meters in length, at least minimally. So these structures, which are huge, provides a lot of stability and a lot of inertia against wave action. So they are ideal to create artificial land on the sea.
Yes.
Whereas the small floating structures, they are obviously susceptible to a lot of pitching motion, rolling and surge, as well as heaving, because it is so small. It kind of pops up and down together with the waves. But when you are very, very large, the waves becomes very, very small compared to the structure, and they are like ripples, like small little ripples on the structure. Yes. So the effect of wave motion is pretty much reduced dramatically. If you stand on very, very large floating structures, you wouldn't feel that you're on the sea at all. You feel like you're on land, Yeah.
I saw that you went to a floating structure in Japan that is 1 kilometer long length, and the width is from 60 meters to 100 meters.
Yes.
How do they make it change the width like that, from 60 to 100?
Oh, okay. You're referring to the mega float, which the Japanese built in the year of between 1995 to 2000.
Yes.
To investigate the feasibility of a floating airport. So the Japanese built this mega float from steel. And what they did was they created modules of them in different shipyards, and they are towed to site and assemble on the sea by welding. They weld the pieces together. So when they come in different sizes, as they're welded together, they can form to any shape that you so wish. In fact, the speed in which the construction of this 1 kilometer long floating runway, test runway, surprises me and a lot of people, because they're able to do it within a couple of months due to the simultaneous construction of different parts of the floating structure at the same time. If you look at a building on land, they are built in sequential. You got to build you have to build the foundation first, and then you build the structure on top of it. So everything in sequence. But for a floating structure, you can build everything together at the same time. You can build the modules as well as the mooring system at the same time. You don't have to wait for one component before you build the other component. So that speeds up the construction of very large floating structures. And that would be very good for monetizing your return of investment, speed up the return of investment. Yeah, you can start operation immediately.
Why do you think Japan is so prone and so open to very large floating structures? Because I saw that they even have a large floating structures association.
Yes. Well, Japan, as you know, is an island nation. It's surrounded by ocean and seas. And interestingly, the Japanese are not equally distributed throughout the whole country of Japan. Their population are concentrated in cities, and most of the cities are on the coastlines.
Okay.
Yeah. So as a result, the land prices skyrocket as more and more people move towards city. So although you have land, you are not utilizing your land in evenly manner. Everybody is concentrated in a place, and when the land cost goes up so much higher, then putting housing, piers, leisure activities, and so on the sea makes sense, because these days the cost of building a floating platform is approximately US $100 per square
Really?
square foot. Yeah, that's right.
That's really cheap.
Yeah. So if your land is much more expensive, it would mean that it's cheaper to go on the sea. Yeah.
Exactly.
So things are changing as a result of demand. As there's a greater demand for the city space and city being constricted, things will flow onto the coastline, onto the sea, or rivers or lakes, for just purely economic reasons.
And besides floating, landing, airports, what other examples are there for very large floating structures? Because I've seen hotels, restaurants, docks, theaters. What else can we do floating?
Yeah. Well, apart from all that diverse applications you have just mentioned, I'm amazed that every day I read about someone thought of a great idea or have already built some of these large floating structures for all kinds of applications. One of the incredible things recently I read was that they built a kind of a surfing dock for surfers to run along this floating structure and jump into the waves while running. So it's like a launching pad for surfers who wants to catch the wave. So they wait on the floating platform. The floating platform are very, very flexible. So they wait. So when the wave comes, of course, it creates. Right? So when they create a wave, they run along this flexible floating platform, and then at the end of it, they jump out into the wave and is right on the wave. Another interesting thing is that Germans built what they call the first floating surf pool. For surfing, they instead of swimming pool for swimming, they created a pool for surfing. So there is so these waves they put it out in the sea. So you pump the sea water and then create this wave, and then they are surfing inside there, even though there is no surf outside, complete calm, but inside the pool you can surf.
Wow.
So you can surf all year round.
That's amazing.
New York City have built a floating prison, a floating prison. They can put about 870 inmates in there. And floating prison is fantastic. You can't escape.
No.
In the middle of the ocean, you can't escape. And of course, I think Rotterdam has built a floating dairy farm. Yeah, that's exciting. South Africa had built a floating bicycle track in their bicycle race. So they let the mountainers, the mountain riders on the motorcycle or bicycle, and then they go down to the lake. And then while on the lake, they cycle on this very, very narrow path, floating path, and create a very exciting track for them. Yeah. You can also do, China create a boardwalk.
Yes.
Longer, 2 times the length of Manhattan, and they brought a lot of visitors there. So it's endless. I mean, they keep on thinking about new things of doing things. Maldives is creating a 18-hole golf course, a floating golf course.
Wow.
Singapore is thinking of storing fuel in the sea. creating floating fuel storage facility and bunker supply system based. The Japanese have thought even a skyscraper on a floating platform, a 1 kilometer. They call it the green float. It's beautiful. If you go to the website, you can Google for the green float. You can see this humongous 1 kilometer tall skyscraper. Of course, the base must be 3 kilometers. So you get stability. And they have already designed it. And it's got approval from the classification society. And they can build anytime. If you want to build a smaller version of it because it is too costly, too high, you can have a smaller version. They can scale it down for you. And it'd be great. Actually, Natalie, if I got money, I would love to, purchase such a structure. We can make a lot of money. All of us form a consortium and create this beautiful floating city out there. And I think a lot of people will flock to that place. It's going to be a attractive magnet to pull everybody in. Yeah. So floating structures has a lot of possibilities to, we can use floating structures to clean our sea environment.
Yes.
We can use floating structures, farm fish, create jobs. We can do a lot of things. Yeah.
Wow.
It's up to your imagination. Yeah.
I know another very cool use that you didn't mention, and it's related to you actually. So I know you have a 60 million Australian dollars grant from the Australian Research Council.
Not 60 million, 600.
600, sorry, 600, yes. 600.
Yes.
So,
we are looking at this. I got this, they call it Discovery Project, which the Australian Research Council, they give funding for some interesting ideas, some novel ideas. So we propose creating a floating forest.
I love
yeah. And why do you want to do that? Because as we notice that a lot of, whenever I look at news, I notice that when there's a storm coming, and the storm is usually characterized by high waves and very strong winds. Yes. And what do people do? They just hunker down. They board up their houses. And they go down to the basement and they pray and they evacuate the city. They couldn't do anything. They just stay where they are, hunker down and hope for the best.
Yes.
I thought to myself, why should we be at this mercy of this nature? Can we do something about it? If you look at the port terminals, when there's a very strong storm, strong winds of more than 40, 50 meters per second wind, you can see these containers are lifted up, literally the empty containers lifted up, and they're thrown like matchboxes, all over the place. And imagine, and the port has to be shut down for days because, they have to clear the containers and so on, and the stacking up has to be secured before they can receive further containers from ships. That's a great loss of money. So I thought that perhaps if we can reduce somehow the wave height and wave energy, as well as the wind speed, bring it down to a manageable level, not to cancel it completely, but to reduce it to a level that our system on land, on shore, and on beaches and so on can handle those kind of wind speed and wave height. Then we could get away with worrying about being destroyed or being damaged, as well as loss of the economy and so on. So I was thinking, then we need a wave, we need a floating breakwater to break the waves, but we also need a windbreaker at the same time.
Yes.
What I'm going to do is I'm going to create an artificial forest.
I know it.
At the same time, create a novel floating breakwater to break the wave. Then I'm going to put the forest on top of my floating breakwater so that I can break the wave, and also I can break the wind. So if we can do both things, then we could survive this storm. And why shouldn't we do that? We have the technology to do so. So I'm looking at the ways of doing it. We have some conceptual design, but that is still in its infancy. We are testing it out, doing numerical simulation and also model testing, and we hope to file a patent for such a floating forest. So Natalie, you'll be first to see it when finally I have finally sorted out all the technical aspects of it. Yeah. So we are discussing about it as well with the Koreans and also with my fellow colleagues who is a wind expert, and also the Koreans who are both wind as well as wave experts. So we're trying to improve on our concept plans and see how we best do it in the most economical way. Okay.
I love it. Do you think it'll be finished by May?
No, not that early. We were given this 4 years to finish this project. We have passed 1 year, so the concept is already the first stage, the first version of this floating forest is already thought through, and we have proven that it can reduce wave and wind. But what we'd like to do is to find it. We want to optimize it and get it more cost effective. And we still have to figure out the mooring system, how best to use, what kind of mooring system to hold the floating forest in place.
So it will be located in the coast of Australia, of course, right?
Yeah.
Because it's
Australia, but a very, very long coastline. So it is pounded by the Pacific Ocean waves. And when you are here next month, you will go to Gold Coast and enjoy this one of the most beautiful beaches in the world, the Surfers Paradise. And what we are facing is that sometimes these beaches, they can be completely destroyed in the sense of being carved out completely. The whole entire beach can vanish in a big storm. Now, when you have a town that is so dependent on the beach for survival to draw the tourists and all peoples of all parts of Australia to that particular location. If you lose your beach, you lose your attraction immediately, and that would mean a great loss in the economy of that town. So they have to rebuild the beach. Each time it's been washed out.
Whoa.
They have to carry sand and bring it back and create the whole entire beach. Yes. Otherwise, there's no beach, there's no fun. That's the fun of that, no beach. So every hotels, every shops and all that depends on the beach to survive. So we can have a floating forest to mitigate or to reduce the wave forces impacting on the beach. We can make the beach survive, even in the greatest storm event. Yes, and also our ports, Brisbane Port and so on, they're subjected to high winds, and each time there come high winds, we have there's a lot of damage. Not only roofs are blown out, the containers are all thrown aside. So we can also protect our ports. That'll be good as well. So that's the idea. Not only in Australia, but many parts of the world, like Bangladesh. If you look at Bangladesh, there's a lot of people perish during a very, very big storm because the waves goes right through not only the beaches, but they go on top of the beaches, all the low-lying areas, because it's very flat in the Bengal area, and a lot of things are destroyed. People are destroyed. Homes are flooded. Now, if we can maybe even mitigate 50% of this damage, is tremendous amount of savings, not only of property but of lives. And Taiwan, for example, Taiwan is buffeted by a lot of big typhoons coming from Philippines. They form it and they move towards Taiwan. So the coastline is always hit by such a strong wind, and they destroy a lot of things. And people die too because of flying debris. So if you can mitigate the wind. For example, you can bring a wind from 50 meters per second wind down to 30 meters per second wind. Then everything will survive, because all structures are designed for 30 meters per second wind, but not many structures are designed for 50 meters per second wind. not many structures can survive.
I understand.
So 30 meter per second wind, if we can get it to that wind speed, we should be okay. And floating forests, we have done a preliminary analysis, and yes, we can get down to about 30 meter per second wind, around 50 meter per second wind. So we are hopeful.
I love it. How about the biodiversity? How will you decide which species to populate the floating forest with?
Oh, these floating forests are not organic trees or whatever that we are, or plants. These are actually tree-like concrete structures. They are just like tubes that comes out from the surface of the floating water, but we call it trees, kind of in inverted commas. So they form obstacles, wind barriers, and they are made of angular sections to create a lot of turbulence to dissipate the energy, and their surface is rough. So we do not make it smooth or circular. We make it purposely the other way around, rough and up. So we call it trees, but it's like a man-made kind of forest in a way. It's not natural grown forest trees, but artificial forest.
Artificial forest. Maybe they can be painted in a way that it's like an art installation, and people.
Oh yes, you can. Yes, you can make it. You can beautify it, and you can make it look organic, and so on. But essentially, they are concrete. Or it could be made of steel, or they can be made from very high density polyethylene or some materials, man-made materials, and they shape into whatever configuration that will cause a lot of dissipation of wind energy as the wind pass through. Yes.
So the computer simulations that you are doing is to test which shapes.
We like to find out how the trees structure look like, how they should be spaced apart. What is the width we should be having, things like that.
I love it.
Yeah.
So you mentioned beaches. There's also a case in Norway of a floating beach.
Yes, in Stavanger. It's Stavanger in the city of Oslo. There was an old warehouse area, and nobody used it actually. And until the developer took hold of this area with the blessing of the city council, they built a new condominium, and they could increase their plot ratio if they create more land. So they created this beach to allow them to build more apartments, and the apartments actually are very, very attractive to the Norwegians because they like to be where the young professionals are located. So these are all young yuppies, they call it, and they stay there. And then because there's a beach, it adds another attraction.
Cool.
So this artificial beach is just a pontoon with sand, and it encloses a sea space in which they can swim during summer. Yeah, and to the Norwegians, it is it's a pleasure to be able to swim in the sea, because generally it's cold most of the time. So in summer, they love to be if they can. That's why you see a lot of Norwegians flock down to the southern part of Europe and also to Singapore, they like the sunny weather. But if you've got a beach in front of your house, fantastic!
Yeah,
you can just
I know it.
Yes, which is quite rare in Norway. So that is another novel idea of the use of floating structures to create floating beaches.
And floating underwater tunnels, which they are also going to build in Norway. I think it's
yes.
I don't know how to pronounce it. Yeah. Very in the most of North.
I will describe to you. The Norwegians are building a 1,330 kilometers E39 highway from the northern part of Norway, and this highway will go along the Atlantic coastline all the way down to southern part to Aalborg. So this particular long highway, they call it E39 highway, have to pass through many fjords, many fjords. Now, of course, how to get through a fjord? you can use a suspension bridge, was one possibility, but the suspension bridge has to be tall enough for the cruise ship to pass by.
Yes.
Or you can use a ferry to bring you across, but the ferry is slow and it can only take a certain number of cars.
Yes.
Or you can build a subsea tunnel. That means a tunnel that you dig underneath the fjord seabed underneath and then go up. But then to build such a subsea tunnel, you need to have a very long road tunnel because you cannot just go down very fast. The gradient is too steep for the motorists. You need a gentle gradient. So that means you must take more and more land on either side to make the gradient allowable for cars safely to go down, right? But this is very costly. But you can shorten this tunnel if you, instead of going down under the seabed, you go through the fjord at some specific height from the surface. All right. So this tunnel is floating, but it's submerged. Why is it submerged? Is because you want the cruise ship to pass by freely. So he must be below the draft of the cruise ship. So he must go below, but not well below, so that they are in a position now. To keep it in position, they have to use tethers. These are cables that holds it down and anchored to the fjord's seabed to keep it in position. Alternatively, if they make it heavy, they can suspend this floating tunnel using floaters on top. So there are floaters like rectangular blocks that are completely void, so that they can have this buoyancy force. And then you have a cable that's attached to this to your floating tunnel. So the floating tunnel is suspended. So there's a new concept, and I believe they haven't built yet, but I believe they're going to adopt this concept because it is very cost effective, and they have done a lot of work in SynTech and Marintech as well for testing this floating. They call it submerged road tunnel. They're going to do it, and they have all the technology and the know-how to do it. So I'm excited. One of these days, you'll see the news being broadcast that Norway is going to do this.
I am going there in January to Longyearbyen. How do you pronounce it?
Longyearbyen. Yeah, that's the area where they take people from there to go and look at the northern lights. Yes. So they're going to build a floating, I believe, a cruise terminal there for the cruise ship.
Yes.
But the Norwegians are experts in floating structures because they have been contending with the sea for a long time.
Yes.
They are able to extract hydrocarbon from very, very great depths, and they have built subsea structures, and also one of the largest platforms called the trolls. They are about 300 meters high in concrete, and they move them, floated out. And it's a gigantic sight to see such a 300 meters of concrete tower floating on the fjords as they pass to the location that they put in the North Sea. And that's where they put the platform on top, and then they will drill for oil, and then they use the big columns that they have for storing oil in there. So it's very, 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 very creative. Yeah, I can see the passion of the Norwegians to try to use floating structures, and they're using floating structures now to farm the salmons. The salmons right now, they are farmed in fjords. They use a circular floater, and then they have a net, and they put a salmon in the net and farm it. Okay. But while they're farming the salmon, what happens is that they're also farming sea lice, and these sea lice are a nuisance, a pest. It sticks to the gills of the salmon, and they suck the blood of the salmon, rendering the salmon almost like half dead, or if not dead. And they are losing a lot of salmon. The salmon production is dropping because of the sea lice. So what they're doing now over there is to build concrete tanks, and then pump water 14 meters below the water surface, which do not contain any sea lice, because the sea lice only on the surface. So they pump this water from 40 meters below the water surface into the tanks continuously, and they farm the fish inside the concrete tanks. So now a lot of them from offshore industry, because of the collapse of the oil and gas industry, a lot of them moves into doing all this fish farming, aquaculture. Now, I think, if I'm not mistaken, they are the number one product that is been exported out from Norway. Is actually salmon. Yes. Salmon is the main exporting produce. So they are going in a big way. In fact, they are looking into completely offshore floating fish farm. They built a gigantic cage, putting this cage about 40 kilometers off from the shoreline, so there's no sea lice over there. And then they are farming using some kind of automation. Everything is self-automated, and they feed the fish and all that stuff. And they're going to build, if successful, they'll build a lot of this giant fish cage all over and farm it out in the open ocean, which gives you better water quality, and the fish will be stronger, and it has better nutrients, and they don't swim in the waste, because if you farm in the fjords, after a while, you swim in your own waste because it's contained. You don't have flushing of your entire net. Yeah. So I think the Norwegians are setting a trend for this fish farming. So a lot of people will be observing them and see how successful they are. And if they're successful, I think there'll be a great demand for such a floating offshore floating fish farms.
I think so, because if the main global exporter of salmon does it, people will definitely follow.
Yes.
Wow. So I know that there are two types of floating structures. We've mentioned already different examples of both. Can you tell us which is the difference between the semi-submersible ones and the pontoon ones?
Yeah. Okay. So yes, you can categorize floating structures into two types: the pontoon type and the semi-submersible type. In the semi-submersible type, is you put a platform, the platforms is raised above the sea level using column tubes that gives the ballast, and they are usually raised above the maximum wave height, in addition to your maximum payload, so they can work out what should be the height. It should be elevated from the surface. So even though you put a maximum load and the maximum wave height occurs at that point, you are still above the water level. You do not want to have this water slamming on the deck, because that will ruin your things and so on. So that's a semi-submersible. They are usually deployed in very high sea area where the seas are much rougher. But if you are putting a floating structure in a very, very calm sea state condition, very benign sea state condition, where the wave height is not more than 2 meters or so, then you can just put a pontoon type of floating structure, which is just the whole platform just resting on the water surface. So for example, like the seasteading, you're looking at your floating island in Tahiti, inside a lagoon. You don't need to use a semi-submersible. A floating pontoon suffice. Yeah. And so any sea state condition that's benign in a harbor area, in a cove, in a lagoon, or in a lake, floating structures need not be necessarily on the sea. It can be any water body in a river, in a lake.
Yes.
Well, you can use a pontoon type, which will suffice, and it's cheaper. You don't need the column tubes ballast, and the whole floating platform rests evenly on the water surface.
I love it. And what type of mooring systems are there to sustain them in place?
Okay. Yes. One of the key components of a very large floating structure system is the station keeping system. The station keeping system restrains the floating structure in the horizontal direction, in the horizontal plane. In other words, we
Okay.
do not let the floating structures to move freely anyhow it likes
Yes.
along the water surface. It's kept in place because it's humongous. If you are moving like this, it's just an elephant in a glass factory or in a Chinaware area.
Uh-huh.
It will destroy everything.
Yeah.
So anyway, this station keeping system, however, does not restrain the movement of the floating structure in the vertical direction. So it allows it to move them down due to tidal variation or due to different payloads. So it only restricts against horizontal direction. So how do you hold something? Just think for a moment, how do you hold something floating out there? You need something like a reaction wall or something to, something that will be anchored down to the seabed, all right? Yeah. So this kind of things are called station keeping system. Now, one of the simplest and cheapest way of a mooring system is to have a single chain, and tied to a heavy sinker, could be a concrete block. So that is attached to your floating structure. That will hold it in place. But obviously, you need more than just one because you need to create redundancy. Because just in case if it breaks, it's gone. So you usually have several mooring lines to hold the floating structure. But for a ship, for example, when a ship anchors in the anchorage area, they only have one chain.
Yeah.
It's called a single board mooring system, SPM. So you can imagine a ship 150 meters in length, and then the chain is about 150 meters in length. There's 300 meters in length, and because it is a single mooring system, when there's the current changes, the ship will just pivot around that same point. Yes. Can you imagine the amount of sea space they utilize to moor, because you must allow for this kind of swinging action. But for a floating structure, we do not want him to swing around everywhere. So we try to hold it there. Okay, so you can use more mooring chain and sinkers to hold it in position, but it still allow it to move a little bit. But if you do not want it to move at all, then you've got to use much more robust station keeping system, such as using, for example, a caisson. A caisson is just a box that you can float out to where you want it to, where the floating structure is to be located. You sink this concrete block, you can fill it with sand or even seawater, you can fill it up. And then you sink down, but you prepare the seabed. The seabed must be hard. Otherwise, if you sink this heavy concrete block down there, it will start to move. So you got to first of all prepare the seabed and sink it down, and then you put your mooring rubber fenders next to the position where your floating platform will be in contact with the caisson, and that will provide a reaction wall. The rubber fenders will be able to absorb the energy so that not all the force goes down to the caisson. Otherwise, your caisson will be so huge if you got to do that. Yeah. So, and you need to resist the horizontal forces, because in the floating structure, there's nothing to resist the horizontal force due to wind, current, and waves. Mm-hmm. So the only thing that resists is the reaction wall, the caisson. So you need the caisson. But if your ground, your seabed is not hard enough, it's soft, then you cannot use caisson, because when you put a caisson, it just by gravity it sinks down, and that would be detriment to, you can lose your whole entire caisson and say, where did it go? So you need to use what we call a jacket up, pile jacket system, and they pile it down, they pile into the seabed, into the hard rock. And then on top of this frame with all the piles there, they put a mooring head. This mooring head will have these rubber fenders, and then we attach a collar around this mooring head, and this collar attach itself to the floating platform like a collar, and it will be held in place. The floating structure will be held in place. So you need to have a few of this, just in case if one fails, the others can hold the floating structure still in position. So you can also have monopile, simple. If the water depth is not too high, you're talking about 20 meters or so, you can pile it down, single pile, and that pile is your mooring dolphin. Then you can put a collar around it. So you get a system of monopiles. But if you go further and further out into the sea and into the ocean, where the water depths are very high, you can't use any of this system that I mentioned, the Kazon or the jacket type, or because when it passes more than 300 meters or 400 meters of water depth, then you go into deep water depth, and you would use tethers. These are cables that goes down to the bottom of the seabed and anchored itself there. So these cables are attached to your they call it tethers, attached to your floating structure. Okay. And the floating structures, it will move like an inverted pendulum. It'll swing back and forth like that. Yeah, but it is held in place. But these are because the tethers, they are very economical for large water depths. If you were to put a concrete or whatever, it's just too much. And then and then on the other hand, if it is very, very, very deep, you don't even bother to put any mooring system. You will put what we call a thruster, a propeller, a thruster in the floating structure that will just move itself like a ship propelling itself. So if it is very, very deep, you do not even have any mooring system. You use a thruster system. Okay. And that will enable to keep its position in around that location. So you might let it drift for a while, and then drift to a place where it's a bit too far from where you are. You can use thruster to, like a propeller, to slowly bring it back to its position.
Okay.
Yes.
Wow. And you have a patent for something called gill cells?
Yes. Okay, let me explain to you. It's a little bit, it's a bit mysterious what's this gill cells. It's not So what happened was that I was commissioned by the Maritime and Port Authority of Singapore to look into the feasibility of having a floating container terminal. I mean, wow. your port terminal, you have these key cranes and stacking yard. So can we, if the water depth is very high, can we have such a floating container terminal? So when I did this study, I hit a problem, because usually you have a lot of loads on the center of your floating container terminal, and that's where the stacking yard is. You put a lot of containers, and these containers are very, very heavy.
Yes.
The containers, the 40-foot container, and they pile up about 9 tiers because they want to save space. They put a lot. So what happens is when you put a lot of load in the center, you get this dishing effect. Yes. The center defects more, and the corners kind of flips out, right?
Yes.
So like this. So then because your key cranes are on the edge, your key cranes, if you have this kind of deflection at the edges, the key crane will not work, because they need to have a zero gradient. Their rail must be very flat. They cannot bend like that. So the crane and your boom is, your boom is 40 meters. If you tilt it, the whole thing, it just cannot work. So therefore, the question is, how do I even out this deflection, right? Oh. So the reason, then that sets me thinking, if you have uneven applied load on the surface, and you have a constant buoyancy force, you are not going to be able to straighten anything on the surface. So what I need to do is I must tweak the buoyancy force. I must disturb the buoyancy force. I must make the buoyancy force also uneven. So how do I make buoyancy force uneven? You can do a few things. You can change the draft. That means you have different depths for your floating container terminal. That means some parts thinner, some parts are thicker, all right? So that you can different buoyancy. The other way is you have many compartment cells. You can flood some of the compartments with water. So you got rid of the buoyancy force. Instead of having buoyancy force there's no longer buoyancy force, because I flood the compartment. But the whole floating structures do not sink, because I flood only certain compartments. So what I do is that if you got a dishing effect, so what I need to do is to flood the compartments at the corners, for example. So when I flood the compartments at the corner, I use the buoyancy force. This thing, as it bends backwards, because of the stiffening effect, this center portion lifts itself up. and become very, very flat. I can make it very flat. By doing proper calculation, I can make it as flat as you want. So, so this idea of flooding a compartment, I gave a very sexy name called gill cells, because they are cells, compartment cells, and they're gills because they let the free passage of water going in and out freely. Wow. There's no active control. So this is something that we could use in a floating structure application, where if your load suddenly, you put one side more than the other side. So your whole floating structure tilts this way. So what you do is you flood this side, so you bring it back to even keel.
The physics.
So in a way,
Sorry, go on.
Yeah, so in a way you can make it evenly distributed. The whole idea is this: in every floating structure, you want it to be as flat as possible. You want the load to be evenly distributed load, so that the buoyancy balances itself out. So the structure can only move up and down nicely without bending. Now, if there's no bending, there's no stress. Stress only comes from bending. If there's no bending, there's no stress. So you can't, there's no cracking. You can't crack something that it doesn't bend. You see, when you bend, some parts are in tension, some parts in compression. If you bend like that, so the bottom part will crack. But if I don't bend, there's no cracking.
Yes.
So there you are. You can make your structure strong and durable.
How is this connected to tunnel liquid continuum dampers? Because I also saw that they are a mechanism for stabilizing platforms by creating a tunnel like this that fills
the Japanese use the thin liquid dampers or liquid dampers on the high-rise building to damp the vibration of the buildings. Now, there's even a better way. You make the fluid, instead of just going from one column to the other column, you have to pass through an orifice. You make a small hole, so the water had to squeeze through it. So that way, you can, by adjusting the orifice size, you can control how much it goes up and down, and you can reduce the movement by a lot. Yeah, liquid dampers is something that it can be considered to reduce the rolling action and so on of the structure. And ships use ballasting effects as well in their thing. So it's like sometimes they say that you got to have if you have some kind of baffle plates that allows instead of water level free edge go from one end to the other, that's very destabilizing. But if you have many walls with holes, then it will stabilize your floating structure.
I can see.
So there's a means of stabilizing the structure.
Something that I saw a lot, that I saw in your work that really caught my attention, is that you are looking into graphene oxide reinforced concrete to increase the strength of the concrete.
Yes, I think this is something that everyone is trying to make concrete as durable as possible. As you know, concrete fails by cracking.
Yes.
So if you do not want concrete to fail, you must prevent cracking. And concrete is very weak in tension. That's why it cracks. So that's why you put steel reinforcing bars to take the tensile forces. So whichever parts of the concrete is in tension, you put the steel bars. So the steel bars take away the tensile forces. All right. The concrete handles the compression. So some people say, well, we put steel fibers in. Steel fibers, they are very, very tiny steel wires they put inside. The fibers redistribute the tensile stresses among themselves. That's also very good. That is at the macro level. But then if you want to go and disturb the cementitious material at the micro and nano level, you need something very, very small. And now we can go to that small level using carbon nanotubes, graphene oxide and all that. What they really do there is, at that level, you see, cracks must start from at some point.
That's what I mean.
Very, very down at the nano level, the cracks start to appear there. So if we can stop it from the onset of cracking at that level, then it never crack. we'll make the concrete very, very strong, because if it cannot crack, it will not fail. So this carbon nanotubes and graphene oxide, what they do is that they have these contact areas where because they're very small, they have all these van der Waals forces and all that. They try to hold on to the atoms, and they're very, very small. So when things want to open up, because they are very, very small, the forces there are very, very great, the atomic forces. They pull them together. They hold it tight. So you can imagine everybody's, you want to pull apart these two persons. I just hold you tightly. And but the moment I let go, the whole thing just goes, right? But as long as I'm there, and the carbon nanotubes are very strong. The tensile strength is 63 gigapascal. And the Young's modulus is 1 gigapascal, very, very high. Several orders that of the concrete. So they're very, very strong, and they're very durable. And they don't corrode. Carbon can't corrode. So they are there to make the concrete very, very strong against cracking. Not only that, because they're very small, they fill up all the void spaces,
yes,
preventing water ingress, and also that they increase the what we call the surface contacts, because they are very small. They go everywhere. They hold things together. So it's like forming a system of cobwebs. Can you imagine cobwebs all over there? So they all tie each other by these cobwebs. The graphene oxide is like cobwebs there. They're just pieces of sheets, very, very small sheets all over. But the problem is this: in this kind of nanoparticles, we do not want them to agglomerate. That means stick to one place. We want to disperse. That's one of the problems. How to make them disperse.
That's a problem, right?
Yeah, on a large scale. When you spread out on a large scale, you want to make sure that they are spread evenly. You don't want to have lumps and lumps of these guys there.
No.
So they have to be treated chemically and all. But these are expensive, because when you start to do all these things, they're very expensive. Yeah. So I think it's still in infancy. We need to make it cheaper and make it easier for full-scale deployment of such a cementitious nano composites, they call it. Yeah. What you want to do is to come up with a kind of impervious, waterproofing skin for the concrete. If you can do that, you solve the problem, because to get to the concrete internally and to the steel to corrode it, you need to go through the skin first, right? So you make the skin impervious and durable. If you can do that, then you solve your problem. So people have been looking at all this. They have Germany and have invented all kinds of skins for these things, and they are, of course, everything will last up to a certain time. Some can only last several years, some can a bit longer, but eventually they will corrode away. But what we need to find is it possible for a more durable skin? If we can do that, that'd be great. And then we don't have to worry about continually replenishing this skin. And but there's another school of thought, because reinforced concrete or pre-stressed concrete, when you deploy in the seawater, they're worried about the corrosion of the steel reinforcing bars or the pre-stressed tendons. So if we can somehow delete that away from having them there, then we don't have to worry about corroding, right? So they think of replacing it with some kind of glass fiber reinforced polymer. They're made of glass fibers. They're very strong. They make into a rod. I can't even bend it. It's very, very stiff. So if they put it there, you cannot corrode. So if you can't corrode, then you can also do this. So you don't have to use fresh water sand. You can use sea sand, even with all the calcium and chloride there, no problem. If you have use seawater to mix with your concrete, there's no problem, because there's no steel for you to corrode if you use glass fiber reinforced. So there is a new idea of people trying to get into this, whether we can use sea sand, seawater, and glass fiber reinforcing bars to build concrete structures for marine purpose, for marine applications. That's something that people are working on. And there's another very interesting discovery. I think there's an American materials engineer, and she studied the Roman concrete, and they discovered this Roman concrete, which is made of some volcanic ash and some volcanic rocks, and they use seawater in the process of making this. Apparently, they form a compound. I've forgotten the name of this compound. It's starting with T, tobalomite or something. It has that kind of name. And apparently it is so strong, it holds the concrete together, preventing any cracks from happening. And that's why they can last thousands of years, incredibly, this Roman concrete. So there's a lot of now studies being made to see whether there could be replacement of this volcanic ash, like using fly ash and other kinds of things, and with other chemicals to make this compound that is so strong. It's like it forms crystal that is so strong to hold everything together. So there's a lot of interesting research being carried out, all with the view to apply it on marine structures to lengthen its design life and its lifespan.
And how does a day in your work happen? Because I know that you model continuum mechanics, right? But do you also do work in the lab? How is a day in your work?
Oh, how's my day in the work?
Yeah.
Okay, I have right now in the University of Queensland, I have a team of 8 PhDs and postdoc fellows, and they are working in different areas. Some work in the area of strengthening of old bridges. Some of the bridges are 50, 60 years old and they need some repairs and strengthening. Some of my students are working in the area of floating fish farms. We are trying to create a completely new concept of offshore fish farms. Another one is, of course, working on the float. Two of them working on floating forests, because one work on the forest, the other one work on the on the breakwater. And then I have students work on discrete lattice models for structural analysis. We discovered that a lot of things down in the nano level are discrete anyway. They are not continuum. There's no continuity on the nano level. Everything is discrete. Even water, you can see they are like, they are a circle of molecules of water. They don't move like a stream. They move in packets.
Yes.
And even gold, and gold, find at the nano level, gold does not behave in a very, very malleable way. It becomes very brittle, and also it's not as inert as people think. It can be a catalyst at the nano. So things changes down there.
Besides improving the tensile strength, increasing the heat dissipation, or being more hydrating, what other properties have you found that concrete reinforced with graphene oxide can have, as opposed to normal concrete that we use in our daily life?
Yeah, of course, we discovered that the mechanical properties is improved a lot. It can also have the thermal properties and electrical properties. Actually, we could. I think that one of the key thing is to make it be able to withstand the onset of cracking. So to prevent the onset of cracking is critical. Yeah, I think that's an important discovery, that we can use nano. Those days, there's no way we can put this nano. We didn't even know such a material exists. But these materials, I think it opens up a new way of thinking, that we can prevent cracking even at that nano level. There's something very, very special.
Wow. What other uses for nanocomposites you find that we can use on seasteads? For example, because graphene sheets are really interesting because they allow the passage of light. They are also stronger than diamond. They are really good electrical conductors. So what uses do you find for other nanomaterials or graphene on seasteads?
it's a very, very interesting paper published in, I think, Nature, either Nature or Science. They use this kind of balls that inside the spherical balls, they have smaller balls in there. Okay. And the balls, when in wave, as they move in waves, inside this ball rub against the small balls, internal balls rub against the external balls, and they can produce, if they're dielectric kind of materials, they can produce charges. So from mechanical motion, we can get electricity out of it. And if you have many millions of this, and they are very, very, there's no in a sense mechanical parts to wear down, because it's just a ball within a ball, and they're made of kind of rubber-like things. So you can generate electricity from that. But the question is how to generate enough electricity. That's what we're trying to figure out, and how far they should be placed so that when the waves come, they just wave back and forth, and while they're waving back and forth, they are generating a lot of electricity.
Yes.
So that's the application of this very small particles inside there as well. We can enhance the amount of electricity we can collect from that. But I think the study of this is going to reveal a lot of interesting applications that we are now at the verge of just getting excited. We don't know enough yet, but as we investigate more and more, we discover we can do a lot more things. Yeah, improve, for example, photovoltaic in terms of efficiency and many other things. Yeah, so they have been used in many structures to give that strength and yet lightness. For example, you have carbon fiber bicycles, race bicycles that can move very fast. They have nanoparticles that they put into clothes that will form a natural canopy, like a forest canopy, that when a water droplet falls on it, it just drop off. Yeah. So it's almost waterproof, and you can wear your most expensive branded, coat around without worrying about being wet.
With no spills.
So these are things that they are doing. A lot of very fascinating.
That would be amazing. So now that you mentioned this, I want to ask, I have here some notes. I don't know if asking this question or not, but I read that single wall carbon nanotubes, so we have zero-dimensional, so we have nanoparticles. Then if you go to one dimension, you have fibers, and then we're talking about a two-dimensional graphene. So single wall carbon nanotubes can dissipate a lot of energy, like you were saying, and you connected it also to its application on seasteads. So this might not be right at all, but do you imagine that we could find a way to use this energy dissipation in the most efficient way possible to, for example, create a platform for a seastead where by people's motion, it can simply generate energy?
Yeah, it's possible that, they are working using dielectric elastomers that allows mechanical action to be changed or converted to electrical energy. The Israelis have put this kind of concept into harvesting energy from roads, and where they have this all this, especially near the container terminal ports, all these big trucks have to go across from one point to another point. So they put all these things. As the truck goes over this, so imagine you get a lot of work done, right? So you do some kind of mechanical action, compressing the material, and then they set up these materials. When they contract, they set up some charges, and these charges are collected, and that's electricity for you. So that is something that we definitely, single wall carbon nanotubes are very good in use in miniaturized electronic systems and so on. So maybe we can use it for sensoring and build these sensors into our miniaturized thing into our floating structure platform that will give a signal telling us that, how our floating structure is performing right now. Am I in stress right now? Which part of my floating structure is very stressed, I can check up and see whether anything wrong with it and come up with a proper remedy for solving the problem. So I think it can be used for sensoring and for for extracting energy and so on. So I think this is still in its infancy. I do not know enough to be able to comment deeply into this thing, but I'm sure that some of my other colleagues in this area of carbon nanotubes will be able to tell you even more exciting things than what I'm telling you.
No, this is already a very exciting for me, and I'm sure for everybody who's listening to us.
Yes. I think there's a lot of things to yet to discover in this area of nanostructures. How to use it in the best possible way.
Well, it's a very young field. It's like 10 years.
Yes, yes, it's less than 20 years.
Maybe.
Yeah, because we never heard of this in 30 years ago. I've never heard of nanomaterials. It's only in the recent times. Yeah.
Oh.
Ajima found this carbon nanotube. So it's only 1991 that this thing appeared. And graphene sheets is even earlier, even more later. I mean, in the discovery. So it's very in its infancy. Now, as we know more and more of this, more such applications will emerge in our newspaper, and we can read about that.
Yes, or in our scientific journals.
Yes, of course.
Yes. We are almost over with the time, but I want to go back to the high-level vision and ask you, why are, or in which ways are floating structures, how do they relate to tackling problems of the nexus, such as energy, water, waste? Why float? Or
yes, these are all top problems that humanity faces currently and in the near future: energy, water, the environment, poverty, and I believe that we can find solution in the ocean if we go to the ocean. Not only that, we can use our advanced technology together as we go into the ocean to find a solution. Now, for example, energy. In fact, we got a lot of energy stored in the ocean. Especially the sun energy is stored in the ocean. Not all are reflected to outer space. Quite a lot has been sucked into the ocean.
yes.
So on the top surface of the ocean, temperatures are around about 24 degrees Celsius if you are looking at the water body between the Tropic of Cancer and Tropic of Capricorn.
Okay.
Usually temperature is about 24 degrees, and they are 24 degrees all the time, day or night. Now, if you go down 1 kilometer below the ocean surface, the temperature drops to about 4 degrees Celsius. So you have a 20 degrees differential temperature change between the top surface and the bottom. So we could use this concept of OTEC, Ocean Thermal Energy Conversion, where we use liquid ammonia, and liquid ammonia boils at a very, very low temperature to about 24 degrees Celsius. It will create a lot of boiling action. And when liquid ammonia boils, it changes to a gaseous state, and the volume expands by 640 times. And when you expand by 640 times, you confine in a chamber, you put in a very small chamber, there's a lot of pressure.
Yes.
So you allow this gas to go through a small little cavity. And then you create a strong jet.
Yes.
That can drive a turbine. And that turbine gives you electricity by turning the turbine. Now, then we take part of that energy that we have extracted and use a riser, which is a vertical pipe, put for about 1 kilometer down to the ocean floor. And we use the energy to extract the ocean cold water, about 4 degrees, rich with nutrients. We pump it up to the top surface. We cool the liquid ammonia back to the gaseous ammonia back to liquid ammonia, and the cycle goes round and round. Not only that, but we also use the water nutrients. The ocean, about 1 kilometer below, there's a lot of nutrients, and that's a lot of food for fish. You can cultivate fish farms as well in that OTEC plant. So you can do it day and night continuously, and that's endless energy, endless. And there's no carbon, no worries about radioactivity. If you're worried about, nuclear plant and so on, there's no radioactivity, no carbon. There's no carbon in the equation. You can also do this. You can also use a vacuum and, put the seawater, and seawater boils at a very low temperature when you have a vacuum. So when the water boils, you produce steam, right? Now you can use steam engine. Steam can use to drive steam engine. And when steam condense, what do you get? You get fresh water. So you get fresh water and you get power as well.
Ooh.
Yeah, so you can use that concept. Now, there's a lot of, I just give you an illustration. You can get a lot of energy from just the solar energy stored in the ocean. But you can also get energy from the wave and from the tidal currents. The wave is endless. If you stand on the shoreline, you see the waves coming, endless, forever. So we can use wave energy converters, with PTOs, push takeoff systems to extract because when your parts that rotate against each other, then you can push the hydraulic fluid, and the hydraulic fluid is able to turn things and so on. So you can get electricity from there. Also, you can get a lot of wind energy from the ocean. Actually, you get more wind in the ocean than on land. So your wind turbine can be made several times more than your land-based wind turbine. They can be huge, humongous. But now the problem is how to make them cheaper. If you can get it cheaper, you can get a lot more power. And also you can have floating solar farms out there because there's no shadow cast on the ocean. You can get all the light that you want, and then the ocean water is cool. So efficiency of the photovoltaic is improved tremendously. So you can get a lot of energy. Then so you can solve the energy problem there. You can also solve your water problem. People fight over water because nowadays water is very scarce, and sometimes it doesn't rain in the right place.
Yes.
And people have to use pipelines from mountains far, hundreds of kilometers away to bring the water to the city. Like Beijing, they get the water from Hebei forest very far away. So in time to come, water is a problem. But if you go into the ocean contains 97% of the water of the world, 97%. The other 2% are in ice caps, and then you got a couple of 1% in the soil, in the aquifer, and only 0.005% that we are using water for our daily use. But 97% is in the ocean. We can use desalination. If you got energy, you can do everything. You can do desalination using reverse osmosis or whatever, or you can boil the seawater and condense the water, and you can get the fresh water. So in the ocean, you can also put artificial reservoir. You can create huge confinement, and during rain, you can collect this rainwater in the ocean. Just like you can collect the rain on the land in your lakes. You can also create freshwater lakes in the ocean.
Wow.
Yeah, you can do that. Also, you can now and also, for example, in the area of creating the jobs, when you go to the ocean, there's a $500 billion industry right now, the blue economy, but it will expand as the ocean utilization gets underway, and more people move to the ocean and take advantage of so much resources there.
Yes.
You can create jobs like building aquaculture farms, sea farms. You can have creation of cities, townships. People are living on cruise ships for weeks on a boat, on a huge boat, and they love it. Why don't you can live there forever if you want? We can create even a much bigger boat. I mean, a flat land that spans kilometers by kilometers. You can jog and do whatever you want. You can have internal lakes inside there, whatever you want.
Yes.
So we can create countries do that. So that will create new jobs and a new way of extracting food, energy, water from the ocean. Those are new jobs. I mean, jobs that are not there, but now becomes available. It wasn't there, but you create something from nothing. So that's great. Yeah, and you know, and food is something that we always, it will be a problem. So as things get more and more polluted on the land, then you know, if you want to go into the ocean, you get very, very clean waters and so on. You don't have contaminated river water and so on. Yes. You can farm very, very high quality crops with fresh water, which I mentioned to you. We're using energy that we extract from the ocean. We can get fresh water and farm our crops there. And they provide food. Not only that, you get seafood, and seafood is very, very, very good for your health. Actually, it's better than eating red. You know? And you don't farm fish on land. It's ridiculous to farm fish on land. People think of farming fish on land is crazy. Let's farm fish in this ocean. It's natural place, and it's clean. Yeah, and the fish grows well in the natural habitat. Exactly. So we can create huge tuna farms, kilometers by kilometers, not restricted by small little space. We can make it very big because the ocean is so big. 70% of the Earth's surface is covered by ocean. There's plenty. Yeah. Even though you take up so much, you still got plenty. It's endless. So I think, by the way, only 5% of the ocean has been explored. 95% is not known. We have figured out there's 230,000 species living in the ocean, but that's based on 5% of the ocean that has been explored. So we believe that at least 2 million species of living animals living in the ocean. Most of them we have not seen or even know of. Every day we see new creatures being found in the ocean.
Yes, that's right.
So this is something very, very interesting, that the ocean contains so much richness of biodiversity that we have yet to know. Yeah. So I think going to the ocean is something that eventually every human being will gravitate to naturally in time to come. If not now, later on, they will figure this out. Because it's a natural progression, from this to that. Yeah. But once we figure out how to create artificial land, we can live on the ocean. Because at the moment, we can't live in the ocean since we don't have gills to breathe and so on. We need to be on the surface. So once we figure out how to live on the surface by creating these pontoons and land, then we can go to the ocean, just like traveling from one point to another on land. We can do it in the ocean.
Exactly. And we can also have buildings that have underwater floors.
Yes, you can have you can have structures, and then you have basement, and the basement goes down into the seabed and seafloor, and that's what will be done in the horseshoe. Is it called a seahorse? No, I'm sorry, the seahorse floating houses in Dubai. They sell each for $2 million or something, $3 million. Okay. And they have this upper floors, and below the master bedroom, it goes down, and then the curtain opens up. They can see the corals, and also Norway has just opened an underwater restaurant where they have a box like that, and they just immerse the other end into the fjords, water body, and so on. That they can enjoy the sea view or fjord view while they're dining. So they have all these things are coming up. Yeah. Very, very exciting times. Okay. So have I answered all your questions?
You have answered absolutely all my questions, Professor Wang. Thank you very, very, very much.
My pleasure. My pleasure.
And
okay.
See you in a month in Brisbane.
We'll see you in a month. Okay. Let me know.
I will. Have a great day. Bye.
Okay. Goodbye. Okay.
Bye.
Thanks for joining us on the Blue Frontiers podcast. To learn more about our work and find out how you can support the project, visit blue-frontiers.com or visit our social channels. You can like us on Facebook, follow us on Twitter at Blue Frontiers, or shoot us a note via our website. If you learned something and enjoyed the show, tell a friend or leave us a positive review on iTunes or wherever you're listening. Don't forget to subscribe to our show and remember to join us for the next episode. See you next time.